Good evening and welcome. Looks like people are filing in here. So I think we'll go ahead and get started. I'd like to welcome you to Mackenzie River Trust HabiChat, Climate Change and Future Flooding in the Columbia River Basin with Laura Queen. My name is Holly McCrae and I'm the Events and Outreach Manager for Mackenzie River Trust, and it is such a pleasure to join you this evening. I have just a few housekeeping items that I'd like to share. When you entered this webinar, the system automatically put you on mute and turned off your webcam. So you are in a view only, listen only mode. And after Laura's presentation, we'll have some time for questions and answers. And to submit a question, use the question and answer button at the bottom of your screen. And please submit those at any point during the presentation as they pop into your brain. We may not have time to get to all of them, but we'll do our best. And if you have to leave the presentation or have any technical difficulties, I'll be sending an email out hopefully tomorrow that will include a link to a recording of tonight's presentation. Before we begin, I want to acknowledge and honor the Indigenous people who stewarded the lands we are on today for many generations before us. Colonization by white settlers drove most Indigenous people away from their homelands, usually by force or coercion. And it's important to acknowledge our past so that we may work towards a more just and equitable future. Our projects and service area include the traditional homelands of the Kalapuya, Siletz, Coos, Lower Umpqua, Siuslaw, Molalla, and other bands and tribes. Today, many of their descendants are part of the Confederated Tribes of the Grand Ronde, Confederated Tribes of the Siletz Indians, Confederated Tribes of the Coos, Lower Umpqua, and Siuslaw Indians, Cow Creek Band of the Umpqua Tribe of Indians, and the Confederated Tribes of the Warm Springs. We understand that having a role in land ownership means we have a responsibility to those whose lands were stolen from them. And the land calls us to commit to continue learning how to be better stewards of the land, as well as better allies to all of the people that inhabit it. I know that many of you who are attending tonight are friends and members of Mackenzie River Trust, and it's so nice to have you join us. Please know we appreciate your support, especially during what has been a particularly challenging year and a half with both COVID and wildfires. For those that are new to us, Mackenzie River Trust is a nonprofit land trust that works to protect the lands and rivers we love in Western Lane County. We have over 6,700 acres of land under our management from the Cascades to the coast. And throughout the year, we're engaged in restoration, stewardship, and educational activities. And I encourage you to visit our website to see all of the upcoming events that we have going on to engage in our work. And if you're not yet a member, please know that a gift of any size makes you one. And I'd like to thank all of the new members who contributed to Mackenzie River Trust when they signed up for tonight's presentation. So now I think I would like to turn it over to our speaker for this evening. Laura is a climate scientist at the Oregon Climate Change Research Institute with a background in computer science and mathematics. Her research interests include hydroclimate extremes and the detection and attribution of observed trends and extreme events to climate change. She is currently a PhD student at Victoria University of Wellington School of Geography, Environment, and Earth Sciences. Laura Queen, please go ahead and turn on your video and your microphone, and I will let you take it from here.
Super. Thank you. I am so honored and excited to be here today to talk about my research on future flooding in the Columbia River Basin. I'll go ahead and share my screen so you all can see. Okay. So the title of this talk and the paper that I'm mostly talking about is Ubiquitous Increases in Flood Magnitude in the Columbia River Basin Under Climate Change, which would be a terrible title of like a novel or something because it totally gives away the answer of what we found, that flooding is increasing throughout the region. Before I jump into the technical narrative, I wanted to talk a little bit about the personal narrative behind this research, which I think is something that often gets left out, but especially if there are other students in the audience, I certainly always appreciated to hear how projects came about and how folks ended up working on them. So As Holly mentioned, I studied math and computer science as an undergraduate at the University of Oregon. I grew up in Corvallis, so that was a big trader thing to do, to go to UO. But yeah, I found myself sophomore year studying math and computer science, not sure what I wanted to do with those things. I just loved studying them until I had this transformative experience at a NOAA laboratory, NOAA being the National Oceanic and Atmospheric Administration. So I applied for and was awarded this scholarship, the NOAA Hauling Scholarship, which importantly came with a 10-week internship at a NOAA lab and mentorship from a NOAA scientist. So I found myself in Princeton, New Jersey at the Geophysical Fluid Dynamics Laboratory, which is a mouthful, learning what a climate model was. I had absolutely no experience in climate science and was totally new to that stuff. But over the course of 10 weeks, I learned that the skills I had been learning, math, computer science, and a handful of physics classes I had been taking, could be applied to this issue of climate change that I was certainly passionate about. And up until then, I, like many other folks in my generation and beyond, felt concerned about climate change, but also unsure of what I could do about it, how, felt kind of helpless. So over the course of these 10 weeks, to discover that there was a place where I could apply my skills to help us understand climate change and work towards solutions, was very exciting. Meanwhile, I was in Princeton. It was so humid, although I understand it's not the most humid place in the States, but compared to Oregon, where I grew up. So I was a little homesick. It was too hot for me and humid. I was learning all these technical, I was on this, technical learning curve. So I decided that I would study my home, at least while I was there. So I would look back and study something about the Pacific Northwest. So that's the very first place I started looking at the Columbia River Basin in a climate model at this lab. And I started learning about the history of flooding throughout the region, learning about the just physical phenomena driving flooding, and became very curious and interested in how flooding was going to change under climate change into the future. So when I returned to Oregon, my NOAA mentor got me connected with folks at Oregon State University, specifically Phil Moe and David Roop, just in case anyone knows the names. And they advised me, and I continued this research as my undergraduate thesis. They hired me after I graduated to finish up the work and get it published. 18 months later, it was a really long, rigorous review process, which was really good. 18 months later, it was finally published earlier this year. And here I am, kind of 3 years later, finally able to share this with people and talk about it. So it's been a really rewarding experience. And so this research project, I'm going to get into the technical nitty-gritty a bit, but it has been a very important experience for me and put me on my current trajectory, getting my PhD to continue to study climate change. And I do intend to come back to the Pacific Northwest after my PhD to keep kind of focusing on this region, and potentially wildfires is my next interest. But I digress. Let's get into it now. If I can, there we go. So general outline for my talk: flooding in the Northwest, why do we care about it? What knowledge are we building upon? I'll get into the methods a bit, and then the results, which is perhaps the most interesting part. And then we can have some Q&A, of course. I want to put a caveat in at the very beginning that I'm expecting some excellent and really interesting questions on the general impacts of flooding on ecology and humans and stuff. And I already want to put out there that I'm probably going to smile and nod and say really interesting question, because my focus, I'm such an early career scientist that my focus is so niche. So I'm hoping we can have some good discussion even within the audience, which would be a lot easier in person, of course, but we'll see what we can do via Zoom. Okay, so flooding, why do we care? Flooding is a relevant, disastrous, destructive natural hazard in the world, but particularly this part of the world. I've highlighted two examples of historic flooding throughout the Columbia River Basin here. On the left, we have the Heppner flood of 1903, which is the second deadliest flash flood in US history. There was a death toll of 247 people and enormous amount of damages, as you can see. And this was caused by a local extreme precipitation event. There's like an electrical storm, lightning, thunder, rain, which just sent water flowing through these valleys of Northeast Oregon. And one of the valleys had Heppner. Heppner is still there today. If you Google, well, many of you may have been there. I haven't been there, but if you Google a photo of Heppner, Oregon, there's this amazing dam just above the town, which is protecting the town beautifully from an event like this. But it's also just this kind of ominous, there's a lot of water waiting there. So it kind of like speaks to this event that happened in the past. I digress. On the right, we have the Vanport flood of 1948, a very different kind of flood. So where Heppner was like a single day event, Vanport was much longer in duration. It crested twice, the flow peaked twice, 2 weeks apart, didn't recede for 20 days, killed at least 15 people, but it obliterated the city of Vanport and displaced over 15,000 residents. Vanport lay on an island in the Columbia River between Portland, Oregon, and Vancouver, Washington. And it was home to the largest proportion of Black Oregonians at the time, and also refugees from Japanese internment camps. So it was a very racially diverse community because they were sequestered there. And this event displaced all of them. So it was horrific, of course, caused physically from a very different place in the Heppner flood. The Vanport flood was caused by warm temperatures, which brought a lot of snow melt, coupled with a lot of precipitation throughout the region. So just a lot of rain, a lot of snow melt, all funneled into the Columbia River and caused this event. But we don't have to look that far back to see examples of flooding in this region. Chehalis, Washington, pictured here on the left, floods quite frequently, often flowing over Interstate 5. In 2019, the Willamette River flooded in Corvallis, flowing over 34. And I don't have it pictured here, but the Umatilla flood event of 2020 was a 100-year flood event as well. So extreme flooding. So flooding, relevant, damaging. We would like to know how flooding might change into the future due to climate change, because if we can predict what's going to happen, we can better prepare for it. So I think this is my worst looking slide. Most of them will not have this many words, but I just wanted to really quickly talk about climate change in Oregon, specifically temperature, snowpack, precipitation, because those kind of directly affect flooding. So I'll quickly go through temperature. Oh, these are all from the 5th Oregon Climate Assessment Report, which just came out a few months ago, the executive summary. So that's where this language is from. So for temperature, annual temperature has increased by about 2.2 degrees Fahrenheit per century since 1895. If we don't do drastic measures to curb emissions, it's projected to continue increasing, and the highest increases for temperature are in this summer. So temperatures going up will continue to go up, especially in summer. This directly affects snowpack, of course, so less precipitation is falling as snow, so there's a slower accumulation, lower peaks of snowpack, and earlier melting. The earlier melting piece is really important for timing of the hydrologic cycle, because runoff can be expected to begin and peak earlier as the snow is melting earlier, which would reduce the amount of snow melt providing water to the system in the summertime and increase it in the winter when there's already more rain going on. But it's complex. That's going to vary geographically depending on where you are in the wider Pacific Northwest. And then finally, precipitation is projected to increase during winter and decrease during summer, generally because a warm atmosphere can hold more moisture. The number and intensity of heavy precipitation events, particularly in winter, is projected to increase. And again, more precipitation is going to fall as rain than snow. So how these things feed into flooding is a complicated question. I mean, you can draw some theoretical lines between, more rain in the winter. Well, that seems like more flooding, but it's complicated because less snow pack and snow melt is going to shift the timing and stuff. So point being, if we want to really quantify changes in flooding, the best way to do that is to use models, which is what we did. So finally, what knowledge are we building upon? People have done this before. They have used climate models and hydrologic models to look at future flooding. Ignore the thing on the left just for a moment, but my point here is concise. One, previous studies have just not considered a lot of simulations. So using just a single model or a single simulation isn't going to give you a measure of confidence in your results, really. And two, the results they did find were varied. So some locations in the basin increased in flood sizes, some decreased. And our study kind of addresses both of these things. First of all, we use an ensemble, so a large suite of future simulations, which actually led us to expect there to be even more variation because we've got more methodological variation. Maybe our results will as well. But instead, we found ubiquitous increases throughout, which I'll show you later. So that differed from previous studies, which really surprised us. The plot on the left is just an example plot from one of these previous studies, which I'm not going to go into a lot, but the point is the flood ratio on the y-axis is a measure of change. It's the future flood divided by the past flood. So if a point lies above the 1 line, that's an increase in flood size. If it's below 1, it's a decrease. And all these points are different locations. So point being, this plot is showing varied results. Some locations are above 1 and increasing in flood size, some are below 1. But I'm not gonna get too deep into it. So moving on to our methods. How do we see into the future? Models. What is a model? It's not that easy to explain, but I wanted to just provide some schematics. The left one here is from NOAA, a schematic of a global climate model. On the right, from University of Washington, describing a specific hydrologic model. Don't worry about the little words or the little drawings. I really just wanted to show a visualization of what a global climate model looks like. So on the left here, we've got the globe. We represent it as 3-dimensional grid cells, which all hold information. They hold variables. Specifically, GCMs, global climate models, are composed of 3 components: a ocean model, which has depth, and so cells that go at different levels of the ocean holding different variables, like describing the chemistry of the ocean or the currents of the ocean. Then you have a land model, which would have elevation and vegetation type and lots of other variables. And then an atmospheric model, which again has height to it, which holds the chemistry of the atmosphere, temperature at the different atmospheric levels. So point being, climate models ultimately are a large set of equations which are solved at each of these grid points, which describe the basic physics of these different systems: the ocean system, the atmospheric system, and land system. And if none of that really made sense, that's okay. The point is, I've heard this said before, maybe you have as well, that we're essentially running an experiment on our globe right now by continuing to pump greenhouse gases into our system. We can wait around, and we are in some way, we're waiting around to find the results of that experiment. But we could also build these models which accurately capture our complex system, and we can use them as laboratories and run experiments in them. And that's basically what we're doing. And the experiment, the scenarios that we give these models are usually a description of how many of our emissions, a timeline of emissions that we're forcing the system with. So for this study, we use these models to We force them with our emissions scenario, and we take from them the large scale meteorological drivers, so the precipitation, air temperature, wind speed, radiation, for example, over our region, and we feed it into the hydrologic model, which is much higher resolution. The hydrologic model has more detailed, describes more detailed systems for our area, especially the Pacific Northwest. It's so topologically diverse. We've got big mountains and valleys and so much diversity of landscape. So having this high resolution hydrologic model, which determines, for each small cell, different vegetative types or different soil types at different depths, base flow, and it captures it responds to the information from the global climate model and shows us how the hydrologic system responds, all the way to routing the water to very specific streams and rivers, and ultimately giving us out time series at specific locations. So I hope that didn't just confuse everybody more, but I wanted just an overarching, these are the tools that we're using to see into the future. This specific data set that we're using was developed at the University of Washington, and it's an ensemble, like I said earlier. So instead of using one model to do one simulation and looking at that, we're looking at an ensemble, a range of future projections. And that ensemble is produced by the combinations of these different choices that a human being makes along this chain of decisions, which is what's pictured here in the boxes. So the first decision you make is the emissions scenario, basically, the representative concentration pathway. I'm going to be showing results for the more extreme emissions scenario, the RCP 8.5. We did calculate the study for both, so we can talk about that at the end if somebody wants to. But yeah, we're using RCP 8.5, excuse me. So that's the information we feed into the climate model. We're considering 10 global climate models, and these are not randomly selected. These are selected because they perform particularly well in the Pacific Northwest, validated against observations. Then we have to downscale that meteorological information to the resolution of the hydrologic model. And there's different ways you can do that. So we've selected here the MACA method, multivariate adaptive constructed analogs. And we chose that because it's more appropriate for extremes analysis, which is what we happen to be doing. It's not that the other one's bad. It's just if we were looking at monthly or seasonal stuff, it would be more appropriate. So we have a single downscaling method. Then that downscaled information goes into our hydrologic model, of which we have 4 choices. There's 2 distinct models, the PRMS model and the VIC model, but the VIC model has 3 independent calibrations. So we're counting it as 4 different model setups. So long story short, basically we have 10 GCMs, 4 hydrologic models, the combinations of which give us 40 individual hydrologic simulations. And a reminder that a hydrologic simulation, the output of that model, is a time series of daily stream flow from 1950 to 2099. And we have 40 of these simulations for almost 400 locations, 396, which I think are pictured here. Yes. So this is the study area. It's the Columbia River Basin, as well as some select coastal catchments. And each of these black dots is one of those 396 locations. So each of these black dots has 40 time series from 1950 to 2099 of daily stream flow. So it's a lot of data, which is good. Other things to point out here, don't worry about the coloring. That's just climate zones, which isn't too related. I guess I'll just go over it. The Columbia River starts up here in British Columbia, Canada, flows north, turns down, flows through Washington, is the border between Oregon and Washington before opening out to the Pacific. We've got the Willamette River, will be a key river we focus on in the study, and then the Snake River as well, flowing through Idaho, up through Hell's Canyon, and joining the Columbia eventually. And I think that's it for that. So I think, I've described the data set. Now, back to our question, how is flood size projected to change? And how are we going to measure that change from these time series? So we defined our measure of change as the discharge ratio. And discharge is just another word for stream flow, just the measure of volume of water passing through a point at some time, usually in cubic meters per second. So the discharge ratio is the ratio of some future flood size that we've calculated divided by some past flood size. So if the ratio is greater than 1, this is the same ratio that I mentioned earlier with the past literature. So if the ratio is greater than 1, that means the future flood size was larger, so that location experiences an increase in flood size. If it's equal to 1, there was no change. If it's less than 1, there was a decrease in flood size. But what do we mean by future and past? So we have to define that. So we experimented with different time windows, but ultimately decided on 50-year time windows. So the past is represented as the snapshot from 1950 to 1999, and the future is from 2050 to 2099. And then how are we defining flood size? Because you could define it like a height or something, but we decided to define it by return period, because that's common in the literature, and also it's really common in normal conversation or in media conversation about floods, defining something as the 100-year event, for example. So the 100-year flood has a return period of 100 years, which does not mean it literally happens every 100 years. It just means that is a stream flow or discharge value with a 1% chance of occurring in any given year. So there's 1 in 100 chance of it occurring in a year. So to recap, really what the main metric we're finding from these time series is that future 100-year flood value divided by the past 100-year flood value, and then that ratio gives us a measure of change. Okay, I feel like I'm cruising through this. So results. We're going to spend a bit of time on this figure because this is the main figure with the main story, and there's a lot going on here. So first of all, each of these dots is one of those 396 locations. So each of these dots is a geographical location out in the world that is likely tied to an actual gauge that's out there, but this is model data. Anyways, they're ordered along the x-axis by centroid of timing. The centroid of timing is the day in the water year when half of the annual flow at a location has passed, which sounds really complicated. Don't worry about it. We're using it as a proxy for snow dominance. So we want to order these locations by some descriptor of their hydrologic behavior. So we've chosen snow dominance. And what I mean by that is a location that is more rain dominant, so towards the left. It has an earlier centroid of timing because a lot of the water in that catchment came from the rainy autumn and winter and early spring months. A lot of its flow and behavior comes from rain, versus locations further to the right have a later centroid of timing. So a lot of their flow is coming from snow melt. So a lot of the behavior in that catchment is determined or driven by snow. So that's the x-axis. The y-axis is our discharge ratio. So I've highlighted 1 with the dashed line because anything above 1 is experiencing an increase in flood size. If a dot is on 1.5, that would be a 50% increase in flood for the 100-year flood in this case. Finally, oh no, there's 2 more things. The size of the dot is the average daily stream flow. So basically a big dot has more water going through it. I'll let you in on a secret already that these big dots down here, for example, are the lower Columbia River. So this is like the Dalles and Bonneville and stuff. So there's a lot of water going through these locations. So they're really big dots versus the tiny little dots that are streams up in the mountain or something. And then the coloring is giving us a measure of spread, because each of these dots is the average of those 40 future simulations we're considering. So specifically, it's the coefficient of variation of those 40 projections. So dots that are blue or purple had a lot of agreements between those 40 projections versus orange or red. There was more spread. And we did these plots for different return periods. I'm showing the 100-year flood here, which has a lot of locations that are orange or red because we were calculating 100-year flood values from 50-year windows. So there's a little more extrapolation going on. But if anybody's interested, I have at the very, very end the results for different return periods where you can see, for example, the 10-year flood. There's a very little spread between the future projections, like everything is purple and blue in that case. So the big takeaway is that every single dot is above 1. So on average, when averaging our ensemble, every place in the Columbia River Basin and select coastal catchments is experiencing an increase of the 100-year flood by 2100. You might note that some of these points seem to be related to each other, like a string of points. And it turns out if we just select certain points along particular rivers, that is true. So watch this string. That string turns out to be the Columbia River, the main stem Columbia. So here we have the exact same plot that I just described, but we just have select locations along the Willamette and upper tributaries like the Mackenzie and the Forks, the Snake River, the Columbia main stem, and then a couple points on Chehalis, since that is a problem zone for flooding. And then the two windows I have here on the top is the results for the 10-year flood, on the bottom, the 100-year flood. And the numbering doesn't really matter, but this is just straight from the paper. The numbering aligns with specific names for these stream flow locations. But the takeaway here is that there are some really interesting patterns that occur along the lengths of these rivers. So not only do we have the story of increasing everywhere, there's patterns of change along these rivers. So the Willamette and Columbia, for instance, as we move left to right, or as we move downstream to upstream, there's two ways you can look at this. One, the points get bigger as you move downstream because there's more water. And also you get more snow dominant as you move upstream, because you can kind of picture the streams retreating back up to the mountains where they start. So reading left to right for the Willamette and Columbia, the increases in flood size grow as you move upstream. So something about the confluence of multiple catchments dampens the increase of flood magnitude. We're still talking increases everywhere, but it's how much it's increasing. The Snake River behaves oppositely for a while. So up here in the upper Snake, as we move downriver, we increase the increase of flood size until the confluence of the Clearwater River tributary, which has a much lower increase and clearly not dilutes. I guess it dilutes the effect of the tributaries up here, but it brings enormous influence to the Snake Water in general and brings the increase much lower in flood size. So really interesting patterns. I think it's, interesting. I'm just going to leave it at that. So moving on from magnitude, we also looked at the changes in timing of these flood events. So what we're looking at here is the Willamette River. 4 select locations, we're moving downstream, up, down. So this is Eugene to Albany to Salem to Portland. And these are called Violin plots. They're showing us the distribution of when these extreme events happen. So you'll remember that for the past here is in blue, we define the past as a snapshot of 50 years. So for those 50 years, we grab the annual maximum daily flow for each of those years. So we have these 50 flood events, extreme events, the biggest flows of the year. We have 50 of those for one simulation, but we have 40 simulations. So we end up having 50 times 40 events, flood events, and the timings of which are represented by these distributions. I hope that made sense. So basically the hump of the distribution here is the day, so this is about mid-February, when most of those extreme events happened for Eugene, for the Willamette at Eugene in the past. So the story here, I'll also note that the dotted lines are the mean of the distribution and the quartiles. The story for the Willamette is there's not a lot of change. The distribution of timing of the past in blue is very similar to the future in green, which is interesting because there was a large magnitude change for the Willamette, but not much change in timing. Very different story if we look at the Snake River. So here you can see the Snake River used to, in the past, really comfortably flood from May to July. But for the future in green, the flood season has shifted earlier and majorly elongated. I mean, some of these tails are really thin, but this is really consistent with a shift of regime. So where the Snake River used to be very snow dominant and the floods would be driven by snowmelt in May, June, and July, clearly there's a shift to rain on snow regime to just rain driven flood events, even changing the timing dramatically. So it's this regime shift from the temperature change, from climate change. So yeah, so for the past, I would say, May to July, the future here, our results are comfortably January, February through July. I don't know if I would count the December tails, but there's like one event there. And you see the same thing for the Columbia as well. So for the Willamette, if it's representing rain dominant catchments, that story is big changes in flood size, very little change in flood timing. And the story for these more snow dominant catchments is change in magnitude, lesser so downstream for the Columbia. But the bigger issue might be the change in timing and how that's managed by the current infrastructure that we have for flood control. So I hope I haven't flown by way too fast. No, I think I'm good. So because I'm at the conclusion point, although I've got all these fun slides afterwards, if anybody has any questions about even more nitty gritty. But to conclude, we looked at a large ensemble of future simulations of hydrology through this region, and we found increases in flood size throughout the entire basin. We found distinct patterns of change in flood size along main rivers. And we also, I didn't even write here, but we found these interesting changes in timing as well and regime shift evidence. But really important to note is that all of this work was on the natural system. None of our models included the many, many, many dams and reservoirs and land use and irrigation and different water abstractions that exist in the real world. So this is showing how the natural system is going to respond to a changing climate. But for some of the larger changes, like magnitude increases in the Willamette or the seasonal shifts, there's certainly evidence that this may exceed the ability of the current flood management system. And this is a particularly timely study with, I was going to mention this earlier, but I'll mention it now, because the Columbia River Treaty, which is a treaty agreement between the United States and Canada, is in the renegotiation phase, and they're considering climate change while renegotiating the management of hydroelectric power in the region and flood management. So the hope is, of course, that this kind of study can inform policy change like that, as well as management change within the U.S. Army Corps of Engineers, which manage all of the dams in this area. So I think with that, I'm going to open it up for questions. And thank you.
Thank you so much, Laura. That was a lot of information. I appreciate the graphics, being able to help kind of pick things out there. I do want to remind folks, you can go ahead and enter questions in the question and answer box, and I can go ahead and read those off when those get entered. But I do want to start with one question, and I'm curious, if you were to go back, what would you change about the project? Is there anything that you would have done differently, or something else you would have looked at that maybe you didn't look at?
That's a really good question. I think one of the ways the study could have been improved is using regional climate models in general instead of global climate models. I know why. Well, the first reason we used global climate models is because that was the data that was available. I didn't develop the underlying data set, so it's about using this excellent data, and also because it's really important to sample widely the climate modeling, and there's not as many regional climate models, or there weren't at the time that the data set was created. But in general, again, when we're dealing with such a complex part of the world, like where we live, it's just better to have higher resolution. So that's one way. And there's other techniques that I would have liked to explore for calculating the flood values. As I got to at the beginning when I was talking about my personal story, I was learning so much through this project. And so it's funny for me to look back almost 3 years later and think, wow, I was learning these brand new concepts. And there were other ways I could have done that. Obviously, I was advised very well, and so I feel confident in the way we did things. But I know more things now, so it's a very general answer. But
all right, I have another question for you that just came in. So what would the effect be if the 3 lower Snake River dams were to be removed?
That's the kind of question that is super excellent, and I don't know the specific effects, particularly because I wasn't working with any reservoir modeling and any models that had dams, so I don't know.
Are you aware of anyone doing that kind of modeling right now?
Yeah, so folks in the U.S. Army Corps of Engineers do reservoir modeling and are kind of continuing this work considering climate change using global climate models and feeding it into their specific models to look at how are these changes going to manifest on the real world, because we need to know that to inform changes in management. So there is work on that being done.
Great, thank you so much. So you talk about the, so when we look at the Willamette Basin area, which is where a lot of probably the people here are on, and thinking about the timing not changing in terms of when flooding will happen, but the magnitude will change. And this is another perhaps ecological impact question for you, but in thinking of like salmon populations, we're probably looking or concerned less about flooding as we are when the drought will happen, right? Like when water levels really drop.
Yeah.
Does your modeling reflect that at all? Does it look at when the water levels are lower than what they have been historically at certain times of the year?
Right. So this study really specifically looked at high flows because you were looking at flooding. You could do a really similar study looking at low flows, or if you were more interested in multi-month lows, then you would not be looking at daily data. You'd look at monthly instead, right, is the summer drought, not that it's real drought, but I grew up always saying, oh, it's summer, it's a drought because it doesn't rain much in the summer. So is that going to lengthen? Could absolutely be addressed using this data, but I did not address it.
Gotcha. Okay, I have another one for you here. The McKinsey, a prominent source for the Willamette, seems to come from a vast cold water subsurface reservoir rather than direct snowmelt. Does this perhaps influence the difference you see in the behavior of the Willamette as compared to other systems?
That's a great question. So one of the benefits of using the hydrologic model is that if we just took runoff data straight from the climate models, you wouldn't be capturing any of that detailed base flow or at all. So the hydrologic models do capture it fairly well, but also not perfectly. And so I will speak to a piece of the work that I didn't show in this presentation at all was the validation work. So we didn't just grab the data from these models and assume that they were going to be fine. We compared the historic flows from the models to observations, a specific data set that's created called no reservoir, no irrigation. So it's going to be comparable to the model data. Point being, we looked at extreme magnitude and timing to validate, and the model was consistently underestimating the magnitude of extremes for the Willamette. Not terribly, but there was some kind of magnitude bias there, which we were suspecting was from underrepresentation of the base flow. So I don't know if this is asking you a specific question, but that's a little bit more information just about how that phenomena is modeled.
Thank you. So I don't see any other questions that have come through, but I am curious too. You had mentioned fire being your next area of interest. I'm curious what specific aspect of that would you be looking at potentially?
Yeah, thank you. Well, first of all, the motivation for that is, as you all imagine and understand, I'm sure, having experienced wildfires so close, well, just to our communities this last summer, well, the many last summers, but particularly in September. And also for me personally, I was in New Zealand making the connections that are eventually the reason I'm studying there. I was in New Zealand during the 2020 Australian bushfires is what I'm getting at. I wasn't in Australia, I was in New Zealand, but the whole cloud of smoke passed over us, and so we experienced it anyways. And so within this 1 year, I just was like, my life, not to make this about me, but it was a personal experience of wow, wildfires. And then I looked into the literature and starting to understand the global changes in wildfire, specifically the boreal forest region and the Arctic Circle region. And the specific thing I would want to look at is the detection and attribution of changes in wildfire. So it's really complex, and it's a really hot topic here in this region, especially near OSU with all just the forestry studies. I know it's really complex, but I would be looking at it for parsing out the contribution of anthropogenic climate change to changes in wildfire.
I can't wait to see it. I know it'll be a number of years, but I look forward to that. Well,
it'll probably take some time.
Well, I want to just thank you so very much, Laura, for joining us this evening. It has been really interesting to learn about your research, and I know that you have shared with me a few links that I will share with the participants of tonight's program that they can dive in a little bit more, one being the Oregon Climate Assessment Report, your paper as well, and then the Climate Toolbox, which you mentioned is a great resource for folks that want to explore the actual data from observations of climate models. So I will be sure to send those out as well. And so thank you for sharing those with us. And to all of you who joined us this evening, again, thank you so very much for joining us for this HabiChat. And I hope you have a restful and restorative evening. And Laura, thanks again. Truly appreciate your time.
Thank you.
Have a good night.
Good night.